Well, hello there, Science 10s. We are going to talk about graphing today, and specifically just graphing uniform motion, which we defined yesterday. So if you don't remember, uniform motion is an object that's traveling at a constant rate of motion in a straight line, which is very difficult to maintain an absolute constant speed, but that is what uniform motion is. And this is what it looks like on a graph. It's a nice straight line, as you would probably expect, because you're covering this exact same amount of distance over the exact same amount of time. So we're going to go over this graph and see what else it can tell us. So the two types of uniform motion graphs that we're going to go over is a distance time graph and a speed time graph. So let's start with the distance time graph, since it is a little bit more complicated. So it looks something like this. So a few notes here. When you are making a table of values, this guy right here is always what's going to go on your x-axis. Of course, your x-axis is the horizontal one. And this guy should always be going on your y-axis, which is right here. Okay? So, if you don't know, this is the manipulated variable and the responding variable. Okay? Because, of course, how far you go depends on how much time has passed. So our manipulated always goes on the x-axis and our responding variable always goes on the y-axis. Really, really important for you to note. Now, I want to know what the average speed shown in this graph is. So how do we find average speed? We actually find something called the slope. What is slope? So some of you have taken science, or not science, have taken Math 10, and some of you haven't. And even if you're taking it right now, I don't know if you've gotten to the linear unit yet. So if you haven't, I am going to show you how to calculate slope. So if you know how to calculate slope, you can skip ahead a little bit, okay? If you don't, then you definitely need to stick around. If you have learned it, but you need a refresher, also please stick around. Okay, so slope is rise over run. What does that even mean? It means that it's equal to the change in the y divided by the change in the x. So y is your, of course, vertical values, and x are your horizontal values. Okay, so what we do is we take 2 points on a line, on a straight line, if we want to find the slope. And again, the slope just tells us how steep the line is. Okay, so we'll call this point x1, y1. Just because, of course, we always know the first coordinate we list is x and the second coordinate we list is y. And then we'll call this point x2, y2, because it's my second point. Now, if I want to find the slope, I take the change in y, so here we go. That would, in this case, just be y2 minus y1 over the change in the x value. So that's x2 minus x1. All right, so let's actually do that here. Let's figure out how to find the slope of this line, okay? So we can see that this point right here is at 6.0 and 30. And this guy right here is at 2.0 and 10. Okay. So if I want to calculate what the slope is, again, y2 minus y1. What is y2? It is 30. And what is y1? It's right down here. That is 10. Okay, so the bigger y value minus the smaller y value. And then what do we need to put on the denominator? X2 minus x1. X2 here, since I put this 30 as y2, the x2 has to be the 6. It has to be the one that it goes with it. So that's 6.0 minus, and then of course my x1 is 2.0. Okay, so then we just do our subtraction in the numerator and denominator. 30 minus 10 is 20. 6 minus 2 is 4. And what's 20 divided by 4? Oh, that's 5. Okay, so therefore our slope here is equal to 5.0. And then if you're ever wondering, so in physics, how we're going to use this is then this slope actually tells us something. If you want to know what the slope tells you, look at your units. What were in your y values? Oh, that was meters. What were your x values? Those were seconds. So look at this. This is giving us meters per second. What is that the measure of? That is the measure of speed. So that's the cool thing about distance time graph. It gives you the speed that they are going. So that's what the slope tells us in a distance time graph. It tells us the speed. So if you have a steeper slope, that would be something like this red line right here. That means the whatever has the steeper slope is going faster. So here with the red line, runner 1 is going faster than runner 2 because they have a not as steep line, of course. So runner 1 could be our rabbit here and runner 2 could be our poor little turtle, but that's just how it goes. So that's really, really important to know. When you have a steeper slope, meaning it's going up faster, it's faster. If you have a shallower slope or a smaller slope or something that's just a little bit flatter, the flatter it gets, the slower the thing is going. Okay, and then of course we have speed time graphs. So we just went over distance time graphs. So distance time graphs are so important because the slope tells us the speed. So we're going to be finding slopes of these lines a lot. Okay, and so you do need to be able to look at a graph like this and say which thing is going faster, runner 1 or runner 2, which is of course runner 1. Okay, so that's distance time graphs. Speed time graphs are actually pretty easy because if we're talking about uniform motion, what do we know? We know it has to have a constant speed. So if we're talking about a speed time graph, there's only one choice. It means that it should be going at a constant speed. Therefore, in this situation, it's always going at what? 5 meters per second. So we changed our y-axis to be speed because time should always be on the x-axis. Okay, so we always have the speed or the distance on the y-axis. So any ideas of what the slope of this graph would be? Any ideas? Well, I'll give you a hint. The slope of this graph should give you its acceleration. What is acceleration? That's how much it's speeding up or slowing down. Is it speeding up or slowing down at all? It is not. So therefore, the acceleration of 0 means it's not speeding up or slowing down. This is also something you did learn in math. You've learned in math a few times now. This is a horizontal line, and the slopes of horizontal lines should be 0. So the slope of this graph is 0. Okay, and that should be true for all graphs with uniform motion, okay? All speed time graphs with uniform motion because the speed is constant. So whatever speed you found, you just draw a line there. So this speed time graph lines up with this distance time graph because we found the slope. We found the slope here was 5, and then we said, okay, well then if I'm going to translate this to a speed time graph, then when on the y-axis, when it's 5, when it says speed is 5 meters per second, I just draw a nice straight line there because, of course, that's just where we're staying the whole time. So let's analyze a few graphs. I just want to see what they are showing. Kind of cut some stuff off here, which is annoying. So this is distance, but we can see that because they gave us kilometers. And this is time. It looks like time of the day. So distance time graph. So we know slope is going to tell us what speed they're going. Okay, so here it looks like they're moving, right? So what's the difference between this line here and then this line? This one, it's steeper, right? So that means they're moving faster. What about this guy right here? What's happening here? It's a straight line. So what basically it means is there's no distance being covered over time. They're just staying 25 kilometers away from where they started. So here, when you see a straight line, a distance time graph, that means they're staying still. They're not moving, okay? And then you can have a negative slope here. It's moving pretty fast, but it looks like it's moving back to its starting point. Okay, so there we go. That's that graph. What about this one over here on the right? So here we have time or seconds on our x-axis, and on our y, it doesn't really show us very well, which is really annoying. So I'm going to put a D there for distance, and that's in meters. So this one's kind of interesting, and this one, you know, you might not really be able to fully understand it until we go over acceleration next week. But if you look at it, it's starting at about 3, right, at 1 second. So we don't even have the full graph. It doesn't tell us where it's at its starting time. It could be straight. It could go back up to 4 or something like that. But at 1 second, it starts 3 meters away. The reason it's starting at 3 meters, that just means it must be starting 3 meters away from whatever the reference point is. And then what's happening? It's moving closer. So if you are, say, at 0 kilometers away from yourself, which makes sense, from here to here, it's moving closer, right? But then what's happening from here to here? It's moving away. And I will explain more why that would be negative in the future. Okay, so finally, I just want to go over a few rules for graphing, okay? Graphing is so important in physics, and I need you to know how to graph. So these are in your physics booklet that are online, but I'm still going to go over them anyways because they're just that important, okay? And I really want to make sure everybody gets them. So here is what your graphs need when you are making a graph. Number 1, a title. Oh my goodness, you guys. The amount of times I've had to take off a mark just because people forgot to put a title is so silly, and we can all do it, okay? All right, so when you're writing a title, it should tell you what the graph is about. For example, the effect on cola intake on attention span of a child. There's no wondering what that's about. We know what that's about, okay? But when we are looking at distance time graphs, I always want to make sure that you always have distance first and then time. Distance here, so for example, if you look at this title right here, this is perfect. Distance traveled by a toy car over time. So what we always want here is distance versus time. Okay, but a distance of what, and then over time. Okay, that's what it should be. And just the same with the speed time graph, it should also be speed versus time. Okay. Number 2 here, labels on the X and Y axes with proper capitalization. So look at this, distance is capitalized, T time is capitalized, and then you need units in parentheses or in brackets. So here distance is in meters, time is in seconds. That has to be there. 1000% has to be there. Okay? The scales on the X and Y axis must be logical. So what do I mean by that? What I mean is, here, look at this scale. Look at how the numbers go up on this X axis. They're going up by what? 4 every time. And is it the exact same interval? Yes, every 2 boxes is going up by 4. So then it's really easiest for us to say, oh, well, then this one must be 2, this one must be 6, this one must be 10, this one must be 14, and this one must be 18, right? So when scales are like that, it's so, so nice. Look at the y-axis, also really nice. Look, this guy's 10, then 2 more up is 20. So it does look like, yeah, every 2 goes up by 20, okay? What's a really bad example of this is this. Take a look at those axes for just a second. What the heck? Oh my word. So we go from 4 to 7. Okay, so that's an interval of 3. Already, intervals of 3 are the worst. And then 2 spaces away, we are at 15. And that's an interval of 8. So first we go up by 3. Then we go up by 8. And then we go up by 1? What? And then, oh my goodness, and then we go up. Then we go up by 0.3. That is insane. Never do that, please. Please don't. Wow. It always has to go up by the same number for the same interval. This one's also just a big ol' mess. Goes from 0 to 2 to 20. So this is an interval of 2, and then the exact same distance is all of a sudden an interval of 18? I don't think so. So this is horrible. Please don't ever do this. It's just, no, I don't think so. Okay, so make sure that your axes are nice and well scaled, meaning there's logical steps between the numbers. Okay, please do that for me, please. Thank you. Okay, a few other things. Points are plotted using a single point with a small circle around it. Okay, so if I had a point here, I'm going to do that, and then I'm going to put a circle around it. Now, what if my next one wasn't like as nice and I kind of had to put it like that? Again, you're just putting a circle to say that's your best estimate. Okay, that's all you're doing. A point should be connected with a line of best fit or curve of best fit unless otherwise instructed. So let's say that I have another point there and then finally another point there. So not all these lines line up perfectly. So let's talk about a line of best fit just for a second. So a line of best fit should try to go through most of them, but if it doesn't go through all of them, that's okay. It also shouldn't be too low or high. It should try to go through most of them. And then also never assume that it's going to go through 0, 0. So just line it up as best as you can. You should always use a ruler. I'm not doing that right now, which is horrible of me, but it's difficult on the screen. So it should be something like that. See, it goes through the first 2. This one's a bit above, this one's a bit below, but it's basically going through about the middle of most of them. Okay, so that's what a line of best fit should look like. Should be a good estimate. And then points. Oh yeah. And then we're done. And then a few more things. Graphs should use as much graph paper as possible. So if this is your graph, all your graph paper, you should not be using that much of the graph. Okay, that is ridiculous. Okay, so you should be using at least half of it. So something like that would be much better. Okay, so that means the curve should take up at least 2/3. So if I'm splitting this up into thirds, well, then there we go. That's 1, 2 thirds. All right, and there's your third one. Graph should be done in pencil. So even when you're at home, doing all this stuff at home right now, you still need to be doing all your graphs in pencil because it's way too much of a mess not to. Next, if more than one line has to be plotted, a legend should be included. So, for example, this is where having 2 different colors comes in handy. So say again, we had one guy there. So this is toy car 1. So you should put like a little legend here, a little blue box, and say, oh, the blue line is toy car 1. And then say we had a second toy car and it was like that. So then you should put a little red box there. And then say that that is toy car 2. Okay, because we can, if we have 2 different toy cars, they're going, you know, the distance, certain distance over time, then we can definitely plot both of those. There's nothing that says that we can't. Okay. Oh my goodness, you guys, this one's so important. Manipulated variable always goes on the x-axis. In our case, we're always talking about time being the manipulated variable in reference to our distant time graph and our speed time graphs. Time is always the manipulated, and then of course responding is distance or speed. Okay? So just one last thing, I just wanted to go over this with you because I do find that people sometimes have a hard time wondering what should I do with line of best fit and have a hard time drawing those. So I'm going to draw a few of those for you. So something like this where you do have like these two weird guys up and down here, and it's you can't line it all up, and that's okay. You don't have to. Like I said, never just assume it goes through 0, 0. Look at all the other stuff. How does it line up best? And then if they don't line up, you want approximately the same amount on above the line as below the line. So if I try to like line up these three, guess what? That line is not a very good line of best fit because it's too high. So we need to get rid of that. So this would be an example of a line of best fit that's too low. Sure, it goes through 3 points, but it's missing all of these guys and it has nothing below it. So that's also not a very good line of best fit. So it should try to go through the middle of the data as much as possible. And look, I didn't even go through that many points, but I have a few on top of the line, a few below, and that is what you're looking at. Okay? This next one's pretty nice. Now, this one is kind of weird. Sometimes if all the other stuff lines up so nicely and you just have one that's off, we even just call that an outlier and we kind of ignore it, to be completely honest. If there's only one of them that's just way off, then I just ignore it and I just draw the line. Okay? And then again, this guy could also kind of be like, oh, that's a bit of an outlier. Like all this stuff lines up pretty nicely. But then we have one above and one below. So in this case, I would say, yeah, still go through the ones that kind of line up, because then you still have one above and one below, and that does end up being pretty even then. Okay, please use a ruler on those, unlike I did. So yeah, but that's graphing, you guys. We are going to go over some more graphing when we go over more physics principles next week, but we just want to stick to graphing uniform motion. Okay, so good luck on those workbook questions. You just have to do a practice graph, and I will